Okay, a very good afternoon to all of you, and thanks to the organizers for giving this opportunity to talk about the status of heavy ion physics in India and its future directions. What we do using relativistic heavy ion collisions are studying emergent properties of strong interactions. This is a time evolution of relativistic heavy ion collisions. And as you can see that the system is femtoscale in time and also in size. That makes measurements and interpreting the physics quite challenging. What physics that we do is encapsulated in this phase diagram of strong interaction. X-axis is baryonic chemical potential and y-axis is the temperature. There is a high temperature density phase where quark and gluons are deconfined and chiral symmetry is restored. There is a low temperature density phase where quark and gluons are confined into hadrons and chiral symmetry is broken. We would like to produce this state in laboratory and study its properties. On the phase diagram, if you look at this point here, the white point here, it is the QCD critical point. It is a landmark point in this phase diagram. Why? Because on top of it is the deconfined phase of quark and gluons. Below it is the confined phase. On the right of it is first order phase transition and left of it is crossover. If we manage to locate, or if it at all it exists on this phase diagram, then this phase diagram will become a reality. The Indian groups have been involved dominantly in CERN and BNL-based experiments. And the participation started in early 1990s in WA93, then WA98, STAR in BNL, ALICE at CERN. Our main detectors try to detect photons and muons, but the major contributions have been in detectors and electronics, physics analysis, and theory. Theory part is very crucial in order to interpret and understand our data and to also suggest observables. The community is also growing. We started with a school in 1989. As far as I remember, I had not joined this community. And then we have our flagship international event or the conference, which is ICP QGP every 4 to 5 years. The next one is coming up in Puri, 5th February next year. So the community is also growing. Now coming to what have we learned from heavy ion physics. First, I will start with what does the first principle QCD calculations on lattice tell us. It tells us that at a temperature of about 155 MeV, this transition from a confined to a deconfined stage will take place. So that is the temperature we have to achieve in the laboratory. That corresponds to about 10 to the power 12 Kelvin. And it is the temperature which existed if you follow the Big Bang model in a microsecond-old universe. It's also interesting to note that among the transitions which took place in the universe, this has the right temperature or energy scales which can be probed in the current day accelerator domain. You can actually think of producing this state of matter. On this slide, I saw the importance of having close theory and experiment collaborations. The red points are experimental measurements, and these black points are theory calculations, both corresponding to measuring susceptibilities of baryon number. Experiment plotted as a function of collision energy, and you could translate it to temperature, where you can use theory to calculate. And there is excellent agreement between the data and the measurement. Have we reached temperatures above this? Well, one way to look at it is to measure photons. Photons which are coming from, these are direct photons or single photons which are coming from quark and gluon interactions. This is the distributions, yields of these direct photons as a function of transverse momentum. It is exponential in shape, thermal, and the slope gives us an idea about the temperature, which is well above the critical temperature for QGP formation. Another temperature which we can extract is use the particle yields and try to fit it to a statistical thermal model with temperature as a parameter. And we fit the yields of various kind of hadrons, from pions, kaons to nuclei. The dots are data points, the lines are theory, excellent agreement, and the temperature turns out to be pretty close to the transition temperature. So hadronization happens very close to the transition temperature. So it seems we have reached that temperature, but have we formed quark-gluon plasma? In order to show signatures of quark-gluon plasma, we have to show that the measurements require the relevant degrees of freedom are quark and gluons. They show collectivity, and there should be some device screening-like effect. There are a lot of interesting measurements at RIC and LHC which probe this aspect, and I'm showing two such measurements. In here, we have plotted in the y-axis is just the ratio of the momentum distribution of hadrons in nucleus-nucleus collisions to proton-proton collisions. If nucleus-nucleus collision is a simple superposition of proton-proton collisions, this should be unity. You see a suppression. This is associated with a phenomena called jet quenching. The quark and gluon jets are quenched in a colored medium. So the relevant degrees of freedom to understand these measurements are free system of quark and gluons. Here is again a strangeness production in heavy ion collisions relative to proton-proton collisions. And you see it's above 1, so strangeness production is enhanced. X-axis is some proxy of impact parameter of the collision. Let's focus on these red points. These are 5 mesons, which is a strange hadron, SNS bar, but its net strangeness is 0. So it cannot be canonically suppressed. As a result, this enhancement is mostly coming from the denominator, since phi is not canonically suppressed. So this can also be explained only if you invoke quark and gluon degrees of freedom. Do we have collectivity? This plot shows a measure of collectivity in y-axis as a function of transverse kinetic energy, where x and y-axis are divided by number of constituent quarks, 2 for mesons and 3 for baryons. Several different kinds of hadrons, differing in charge, mass, baryons, mesons, they all seem to line up in one curve. That shows that this collectivity has some common origin, and it is from quark and gluon phase. So it's partonic collectivity. Now, what about Debye screening? We tried to measure yields of JEPSI, again, in heavy ion collisions relative to PP collisions, and you see a suppression. JEPSI is a CC bar bound meson, and this suppression can arise if it is Debye screened by presence of other quarks. So we have seen all these 3 features, and quark-gluon plasma is formed in the laboratory. Now, once we have the quark-gluon plasma, and specifically at LHC, where its duration can be long because we have higher energy density, we can study its properties. So what are the properties so far we have looked at? Here again, you need a very close collaboration with theory to confront with or match with the experimental data and obtain these properties. The first one is shear viscosity to entropy density. You compare viscous hydrodynamic calculations with experimental data of collectivity, and you find that it is these values. Lowest compared to any other known fluid. And that's why the quark-gluon plasma is called as a perfect fluid. We have also extracted bulk viscosity. The uncertainties are large. We have extracted, got an idea about diffusion coefficient. Here it is presented in a dimensionless quantity as a function of temperature. Here are lattice QCD calculations, and the uncertainties are large. It seems that the heavy quark perform Brownian motions in this thermal bath of light quarks. When we collide 2 heavy ions, there are 2 major initial conditions. One is large magnetic field, and large angular momentum is imparted to the system. That could cause polarization of the quark-gluon plasma. We have measured the polarization through hyperons in percentage as a function of collision energy, and there are finite values. If you take the average value of the polarization and assume that the entirety is converted to thermal vorticity, it turns out to be 10 to the power 21 rotations per second, the most vertical fluid produced in the laboratory. We have also got an idea of opacity in terms of a transport parameter, transport jet parameter Q hat. It turns out to be of the order of 2 GeV square per Fermi, indicating a very dense medium has been formed. So these are what the properties of quark-gluon plasma we have studied. Now, what is the status of the phase diagram? I come back to this temperature versus baryonic chemical potential. At close to 0 baryonic chemical potential, the transition temperature is around 155 MeV. Hadronization is close to that, and it's a crossover. That is, QCD calculations suggest it's a crossover. But do we have any experimental evidence that the system is thermal? Now, we have tried to probe the multiplicity distribution of net baryons up to 4th order and found that thermal models are able to explain 1st order, 2nd order, 3rd order, 4th order data very well for below 140 MeV. So system appears to be thermal at least up to 39 GeV from the measurements and theory. What about the critical point? Theory says that if you look at the 4th order fluctuations of net proton distribution as a function of collision energy, it should show a non-monotonic variation. We see a sort of non-monotonic variation at 3 sigma level. Errors are large. We have collected high statistics data last year, and that will reveal the true picture. But what we have done also is measured in fixed target mode at 3 GeV and found that this system is hadronic in nature. It sort of puts a region from the experimental perspective. If critical point exists, it has to be between this part of the mu b, x-axis of the phase diagram. It's between somewhere 200 to 750 if a QCD critical point exists on the phase diagram. Now, let me come to specific contributions from Indian group. This is selected results, and we started with first observation of collectivity in WA93, and then went on to measure partonic collectivity, disoriented chiral condensates, made substantial contributions towards phase diagram of QCD, discovery of anti-helium. Through our photon multiplicity measurement, we observed an unique longitudinal scaling associated with limiting fragmentation. We also saw evidence of spin orbital angular momentum interactions and rescattering effects. As I said, the theory plays a very crucial role in interpreting the data. And there has been very, very major contribution from the Indian theory groups. And this is only some selected results, starting from lattice QCD, where diffusion coefficient calculations, as you saw when I showed the comparison plots, or where is the likely position of the QCD critical point, pioneering work in electromagnetic probes of quark-gluon plasma, equation of state, heavy quark propagation, and currently people are actively working on developing relativistic hydrodynamics, viscous hydrodynamics with magnetic field and spin. These are ongoing developments. This month itself, I think colleagues from India with other collaborators have shown how to put together relativistic spin magnetohydrodynamics framework in place. It's a starting point, and this would be best to understand the data. Now coming to future, the relativistic heavy ion collider program, the STAR experiment, will take data up to 2025. And then of course the data will be available for physics analysis. We have CBM experiment in FAIR. I think that Professor Chattopadhyay will discuss in detail. We also want to participate in the Electron Ion Collider program, which will start possibly taking data in 2032-34. Currently, we are working with the ACCELERATORS experiment at LHC, gearing up our detectors and to cope with the high luminosity, which we will be sampling, as well as improving on pointing resolution, where we will try to focus on heavy flavor measurements to get better handles on transport properties of quark-gluon plasma, reduce the error bars and understand its dynamics better. So in the what are we involved currently is a forward calorimeter effort, which is a sampling calorimeter of silicon and tungsten. And the physics focus is to understand the distribution, the parton distributions inside the nucleon and the nucleus. India is a major contributor to this, this detector effort. In near future, we want to participate in ACCELERATORS 3. ACCELERATORS 3 will be a complete overhaul of the current ACCELERATORS detector. It will have layers of advanced silicon detectors. In fact, it would have wafer-size CMOS active pixel sensors, which will go down to thicknesses of about 30 micrometers, and they can be wrapped in cylindrical way so that the material budget is less. And there we are going to address specifically chiral symmetry restoration and, of course, transport properties through heavy quark measurements. We have already taken data in the beam energy scan program, which will shrink these error bars to this level. And this will give us clearer idea about the phase diagram of quantum chromodynamics in the STAR program at RIC. In the Electron Ion Collider program, it is a unique facility which provides us collision of electrons with polarized protons and electrons with nuclei. It will address some very interesting physics questions, which I will come to in shortly. But there is already a starting of an experiment collaboration forming called as EPIC. And several Indian groups are associated with it, both from theory and experiment. The timeline, as I said, is somewhere between 2032 and 2034. Now, coming to all that I discussed has been put together in this mega science vision document of nuclear physics in 2035. There are 3 sub areas, the one on heavy ions, then low energy nuclear physics and plasma physics. These are the working group members. A subset of them form the drafting group members who have been meeting regularly for last 1.5 years every week to come bring this document, which will be discussed in detail by Professor Amal Dighe. And there are regular consultations with the working group. We obtain inputs from individuals, institute, facilities, collaborations, both theory and experiment. And we prepared the first draft, which was circulated among about 4,000 scientific members across various areas, and inputs were received. Some about 60 written inputs were received, and they were incorporated in a revised draft, which was then discussed by a team of national and international experts. There also we got some detailed 9 comments, and those were incorporated. And the next version of the draft was discussed with the principal scientific advisor. We, in this course of preparation, consulted the STIP document, the past vision document, and long-range plans in US and Europe. I will only tell about the heavy ion part recommendations which is proposed in the draft. This has got to do with this phase diagram of QCD. I again come back to it, temperature versus baryonic chemical potential. The way to access it experimentally is by changing collision energy, you change the X and Y and X axis. LHC is around here, FAIR is somewhere here, and RIC in between. So in order to get this phase diagram, we need to take data at LHC, RIC, and FAIR. And that is the recommendation from this community. And especially in the high density baryonic matter regime of CBM. We, of course, would like to participate in the Electron Ion Collider experiment, not only to address these fundamental questions, but to understand the initial conditions of heavy ions which we are colliding. Now, one other aspect I just want to mention is we have a detailed discussion on industry participation in mega science project. There is in the annexer, there is a list of industries which have contributed to this project. What is heartening to know is that the Indian companies are going beyond that and getting some work from other than experiments. At CERN, for example, these are some of the few examples. So that is a positive trend in that direction from Chennai, Vadodara, Nasik, all places of India, Lucknow, Kolkata, and they are contributing to it. We feel that allowing industry to be directly part of mega science project will be a good thing. Also, we should develop avenues where UG, PhD, and postdoc get industrial experience in industrial setting. That would help them in future, and perhaps supplement existing grant for high risk, high gain research in order to develop some generic technology. There are also features which we have presented in the document, which is cutting across the mega science areas. For example, computing is one where we have recommended petaflop level machines for centers and hundreds of petabytes of data storage and good connectivity. Another important aspect is the National Detector Development Training Center. This is very crucial for our participation in any mega science project. And I think this is true for all mega science project, not only nuclear physics or even not only high energy physics. We should have specific human resource development programs, and outreach is an important component where India has last year joined International Particle Physics Outreach Group. We also have given a timeline. This is so as to see how we have a finite number of people and resources, so how these are spanned out. Keeping in mind that we will be looking at the physics possibility, we will be looking at the upgrades and also planning for future experiments. These are the set of experiments, and they seem to be nicely phased time-wise. So I'll come towards the end. What we are doing is towards a complete test of QCD as a theory. What I mean by that, we have the standard model with Higgs origin of mass. We have tested QCD at perturbative regime excellently. The theory works. This is jet cross-section with jet PT, several orders of magnitude in PT, X and Y axis. We have also tested QCD in the non-perturbative regime at ground state. Masses of hadrons are very well explained with less than 5% accuracy. We have gone one step ahead, non-perturbative regime at finite temperature. There seems to be good agreement with QCD and the experiment, and we are laying out the phase diagram of QCD. We will take all this to one more level if we participate in, we have already started participating in the Electron Ion Collider program, where the four important questions, some of the four important questions are, how do quark and gluons form nuclei? How does proton get its spin, gets its mass, and what is the nature of dense gluon matter? We will perhaps be making a transition from temperature versus baryonic chemical potential to parton density related to 1 by x, and resolution, which is related to momentum transfer square, q square. And we'll see what emergent properties QCD lead us to in this facility. That is all. I would like to thank all the experimental collaborations, the theory colleagues, the drafting and working group members of the Mega Science Vision exercise. And I would like to point out that this month, Alice released a review paper which encompasses the last 10 years of physics which the detector has carried out. Thank you very much.
Thank you very much, Bedanga, for this comprehensive review. And talk is open for questions, comments. Yes, please.
Bedang, I was curious, this phase diagram at one point you said where the ALICE is running and where the RIC is and CBM is. Is there any problem that ALICE was on the top corner, right, left side? That's what, yeah, around 1. That's what you said where it's running. Can it not tune its things to run where the RIC is running? Is it not possible?
Yeah. So how is the question then is how is center of mass energy related to this X and Y axis of the phase diagram? So if you go increasing the collision energy, then you go to higher temperature and lower baryonic chemical potential. If you go to lower collision energy, then it is higher baryon density region and moderate temperature. So that is how it's linked. RIC beam energy scan actually does that, goes from 200 to 7.7. And LHC then covers from 2.76 to 5 TeV. And CBM will then take over from 11 to, I think, 3 or 3 GeV, which to us is the best.
So another quick question is, apart from the critical point, understanding its property, the next big questions is what you put the 4 questions in the last slide. Is that correct?
That is, of course, fundamental questions.
Fundamental questions in future to answer. Thank you.
Yeah, so you mentioned that you plan to study chiral restoration with Alice in the future, if I understand correctly. So what's the observable there?
It is looking at the rho and A1 chiral partners, whether their spectral functions meet or they vanish. But we have to take it with some caveat that we need to, the theory tells us that it's a 10% change, which we will see in experimental observable. So all efforts are there to get the backgrounds and the reconstructions done so that we can see a 10% different with and without distortion. So I just indicated it in one of the plots here, but oh, it's taking time.
So how do you see the changes in the masses?
We will reconstruct the dileptons and have an invariant mass of the dileptons.
Yes, I understand how you can measure the rho mass. But
Yeah.
And the A1, you just assume it's not changed?
Yeah, so we have these spectral functions, which comes from theory. We will have our measurements and then confront it to the data to see if we see any changes.
Okay, I think we should perhaps move on and call on Professor Chattopadhyay for the next talk, India and Fair.